I see. So I should turn this mic on, I guess.
Great. Hello, everyone. Thanks again for joining us for another installment of HotSci. I just want to point out we have special guests today from the JHU Center for Talented Youth. So I hope they get as much information as talk as we all will. And two of our speakers today are postdocs from JHU. Our first speaker today will be Chris Nagele. So let's go ahead and give a round of applause.
All right, thanks. Hi, my name's Chris Nagele. I am a now second-year postdoc at JHU, working with Julian Krolik on predicting X-ray spectra of accreting black holes from simulation, or at least that's what I'll be talking about today. So first off, big thanks to the HotSci organizers for putting this all together and for inviting me to talk about my research. And so let's get into it. So this talk's going to be about black holes, and it's possible that you yourself are not a black hole person. So why should you care at all about black holes? And the basic reason is that black holes are intertwined in many areas of astronomy and physics. So for instance, I first got into the study of black holes because they're the endpoint of the evolution of massive stars. If your star is above a certain mass, it eventually becomes a black hole. And this has all sorts of consequences for kind of our study of massive stars. So we study the black hole population in order to learn about massive stars. We study the massive star population in order to learn about black holes. And one way in which we do this is rapidly rotating massive stars when they end their lives are thought to launch jets and be observed as long-duration gamma-ray bursts. And these enable us to study stellar physics even out to very high redshift. And they might even produce some interesting elements in terms of the evolution of kind of the chemical species. Though right now we don't think that this is contributing to the R process. It's kind of out of fashion right now, but still it will produce some iron and other heavy elements. And black holes are also the study of compact object mergers. So LIGO right now is seeing black hole mergers and black hole neutron star mergers. And these are not only interesting in telling us about the black hole population and the stellar population that it came from, but also they can be used as tests of general relativity. So general relativity obviously has passed all of the tests that LIGO has thrown at it, but maybe LISA or Einstein telescope will throw another more stricter test, which it won't pass, which would be interesting. The other region near black holes, which is kind of thought to be able to use to test general relativity, is very near to the event horizon. And specifically when gas gets very near to the event horizon, one of the ways in which we observe that is by astrophysical jets, which are launched from the black holes. And so these we can observe to learn about the properties of jets. And they also induce feedback into the surrounding media. So for instance, in the study of galaxies, feedback, both radiation feedback and kinetic feedback, kind of this overall injection of energy into the ISM and even the CGM is an important ingredient in learning about kind of the life cycles of galaxies. And we also, when studying galactic evolution, have these correlations which we observe. For instance, the M sigma relation, which tell us that there must be some sort of relationship between the evolution of the black hole and the evolution of the galaxy, even if we don't quite understand that relationship yet. And this takes us to the origin of the supermassive black holes, which is a topic that's near and dear to my heart, because even before JWST, we saw these massive black holes very early on in the universe, and it was a bit of a puzzle how they got there. And now JWST has seen a bunch more, or at least things that are probably black holes, or maybe black holes, depending on who you talk to. And then the final point is that quasars are just observationally useful. We saw this last week, because quasars are very bright and they're very far away. This allows us to study things at high redshift. It also allows us to study things at low redshift, for instance, the structure in strong lensing clusters, and also absorption by foreground gas. Okay, so those are some of the reasons that you might care about black holes. Now, what do we know about these things? By their very definition, black holes are hard to study because they're black. They do not emit photons themselves. And this makes it a bit challenging to study them because as astronomers, our first option is to just point a telescope at it. So what do we know? Or what are the ways in which we can study these somewhat elusive objects? And the first is by using radio observations. We can actually study the material that's falling into the black hole, and we can get pretty close to the event horizon doing this. And the next thing is accreting, or black holes which are accreting at fairly high fractions of the Eddington rate get very hot, and these produce X-rays. And we can look at X-ray spectra, such as seen in this second plot. In particular, this is the X-ray spectrum up here. So this is energy on the x-axis, flux on the y-axis. This is the residual here. And this is a K-alpha line, which I will mention a little bit later. The third plot shows the chirp figure for the first black hole merger in LIGO. And this fourth plot shows the M87 jet, but these two figures, although they're showing the same source, are on different scales. And then the final figure is not an observation. So this is the jet, a simulated jet inside of a star from a collapse star event. And the reason I'm not showing an observation is because gamma ray burst light curves are pretty boring. But there is a lot of interesting physics that goes into producing those few gamma rays that then make it into our telescopes. Okay, so this is a non-exhaustive list of the ways that we can learn about black holes. But what would we want to know if we kind of could know much more about black holes? And the basic thing you want to do is start counting them. So we would want to know the number density, and in the case of massive black holes, the binary fraction. And strangely enough, this is not something that we can do all that well, because as I mentioned before, black holes are not always easy to find. So in particular for the number density, you can count the AGN, or the quasars, and you can make some guess of the number density and the mass function. But then when you compare that to the pulsar timing array data, there's a slight mismatch. So we want to be able to do this a little bit better. You can also look at the spin function of the black hole population. You can do this either through LIGO or by using X-ray spectra, by fitting X-ray spectra to X-ray observations of black holes and trying to infer a spin. And again, these two things do not match. This is probably because the X-ray spectra is very hard to do. And then for accreting black holes, we could, in principle, learn things such as the accretion rate, the composition of the accreted matter, that's basically how much iron is there, and the magnetic field properties. Okay? So this is kind of like a wish list of the things that we want to know about by observing black holes. And then there are also some open questions, which I've listed here, which are more phenomenological, and I'll get to some of those later. Okay, so this talk is about predicting X-ray spectra coming from accreting black hole systems. Why is this a hard problem? So imagine that you are a naive first-year postdoc, and you say, there are plenty of GRMHD codes for black hole accretion. Some of them are open source. Why don't I just download one, add radiation, and we'll solve this whole problem? Now, of course, no one is this naive. No one actually did this. But why can't you do this? OK, so the first step in adding radiation physics would be to say hot gas emits radiation. And we know how to do this. OK? And the second step is, in which direction does it emit radiation? Well, it emits isotropically in the fluid frame of the gas. So as long as you can boost to the fluid frame of the gas, and the gas is swirling around the black hole at an appreciable fraction of the speed of light. So this is something you need to do. But we all know how to do boosts. So as long as you can do this, it emits isotropically. OK, so far so good. Here's where it gets a little bit less good, which is that the radiation field around the black hole is not isotropic. If you have a pocket of hot gas, and you look nearby to that hot gas, say you have a simulation cell, the radiation traveling through that simulation cell being produced in that pocket of hot gas is not going to be isotropic. It's going to enter one side of the cell and go out the other side of the cell, which means that in order to track this radiation, we need multiple angle groups. And this is not good, because GRMHD codes are expensive to run. We don't want to be adding whole other sets of parameters. But if you're able to successfully track the matter, or track the radiation as it's traveling through this simulation, eventually we'll hit some matter. And there, what will happen is an energy-dependent phenomenon. Basically, the high-energy photons and the low-energy photons that hit the same piece of matter will do different things. So now you also need multiple energy groups, okay? And this is really not good. So the takeaway here is it is very expensive to add radiation to GRMHD. And there are a few groups that can do this. So for instance, the Athena K radiation group is running simulations of black hole accretion with radiation, but they have to be very coarse in the way they treat radiation, and it's an extremely expensive endeavor. Okay, so as I mentioned before, we're not running radiation GRMHD simulations, we're post-processing already existing GRMHD simulations with radiation solvers. Okay, so what do you want to have when modeling the radiation near this black hole? You want to have MHD, so you want to know in what layout your matter, in what kind of how your matter is laid out around the black hole and how it's moving. You want to take into account relativity, and you also want to take into account radiation. So thermal radiation, as well as Compton scattering, which is producing a lot of the luminosity of these systems, and also atomic processes, such as K-alpha emission. Okay, so how do people attempt to do this? The first class of models is so-called phenomenological models, and they say, we're not going to care about MHD. MHD is expensive to run. We're just going to ignore it for now and write down some simple assumptions. And if we do that, we can do the radiation pretty well. Not perfectly, but they can do the atomic processes, which is kind of the allure of this method. And they can do the GR pretty well. But the problem with this is you can write down 1,000,001 different plausible density distributions. And it's really hard to discriminate between different physical scenarios using these phenomenological models. So most people, when they're approaching this problem, are going to do some sort of post-processing of simulations. And the simplest sort of post-processing you could imagine is thermal post-processing. So you take your simulation. So now we're taking the MHD data, looking to see where there's hot stuff, and we say that hot stuff produces luminosity proportional to t to the fourth. And then we can take into account all the special and general relativity. Okay, so that is the first thing that you might do. But this is actually not that great because, as I mentioned before, a lot of the luminosity from the system is coming from Compton scattering. So if you're not including Compton scattering, you're just missing a lot of the power. Okay, so the next class of models are inverse Compton models. These come in two flavors. One which shoots photons from a camera towards the black hole system. So these photons are traveling backwards in time. And when they encounter some matter, then you look at the properties of that matter and produce a spectrum in that way. And then there are Monte Carlo codes, such as Pandorata, which shoot photon packets from some surface, and then these scatter off of electrons in Compton scattering events, and then they can scatter multiple times, and so they travel through the system until they escape to infinity. Okay, so this is all well and good, but you can see that we're still missing these atomic processes in the bottom right. And so the next code I'm going to talk about is called P trans X. This was written by Julian's student Brooks Kinch in 2019. And this code does all of the radiation physics, and it's post-processing the MHD data. And the way it's able to do this is by simplifying the geometry of the problem. So we have an accretion disk, and in this disk, we're only considering radiation moving in one dimension, so upwards or downwards in the disk. And if we make that assumption, then we can do all of the radiation physics that we want. So this is great, but it doesn't have the GR and the special relativity. So what we need to do is we need to make these two codes, Pandorata and P trans X, talk to each other, and then this will include all of these relevant effects. Okay, so I've cooked up a little cartoon here. So on the right side, we have a black hole and an accretion disk. This accretion disk is split into three regions. There's the corona, which is the outer region. This is hot and diffuse. And then there's the disk itself, which is colder and denser than the corona. And then at the very center, there's a thermal core. This is where radiation and gas have the same temperature, where they're coupled to each other. Okay, so let's imagine that you're a photon, and your goal is to start in the thermal core, and then to escape this system and reach Earth and tell us something about the black hole system. So you start with an energy of, let's say, 100 eV, and you're traveling out into the disk. What happens next is you might scatter on a few different electrons, which are these black X's. And because you start in the thermal core, which is relatively cold, these interactions with electrons are providing energy, are taking energy from the electrons themselves and giving it to the photon. So the net transfer of energy is towards the photon, so the photon energy gets higher. And now let's say that you escape the disk, and you're traveling out through the corona, but you're unlucky enough to hit a coronal electron. And let's say it's a very hot patch of gas, and maybe it's a very fast-moving electron in that patch of gas. So it smacks you right back the other way, and now you have an energy of 20 keV. And then you're traveling back down towards the disk, and this time you're also going to scatter on a bunch of electrons, but now you have more energy than the electrons. So you're transferring energy from the photon yourself to the electrons. And so after a few scatters, you may have an energy as low as 10 keV. And then after one more scatter, let's say you have an energy of 8.5 keV. But this is bad news for you because you're headed right towards an iron atom, which is this purple sphere here. And what's going to happen is you're absorbed by the iron atom, and you kick out an electron in the iron atom. And then that iron atom eventually is going to find another electron, which is going to emit a K-alpha photon as it fluoresces down to the ground state. So sorry, you didn't escape the system, but this other photon, which is shown in blue, is going to escape into the corona and eventually escape to infinity, modulo some gravitational redshift. OK. So, oh yeah. OK. So what we have to do with our two post-processing codes is take both of these systems into account. And so in the disk, we're using this P trans X code, which can do all the radiation, but not the relativity. And then in the corona, where there are fewer scatters, but we need to make sure that we're doing each one in completely correctly in special and general relativity, then we use Pandorata. And the idea is that we iterate back and forth in between these two codes until we have a converged solution for this whole system. And the reason this is kind of groundbreaking is because it allows us to solve for local thermal equilibrium in every point in the simulation domain, which produces significant power. So this is showing temperature maps for both the corona, which is outside this black dashed line, or dotted line, and the disk, which is inside the black dotted line. And so this is 10 solar mass at 1% Eddington, and then this is going all the way up to 10 to the 8 solar mass, and then on the right side is 1% Eddington. And so this first figure is what's been done in previous work, essentially, and this is already much more advanced than any other post-processing code, which really struggles to solve for the temperature in the corona. But now we can go beyond that by also solving for the temperature in the disk. And once we've done all this and converged the whole system, we also get the spectrum. So this is, let's see, this is energy here on the x-axis and luminosity in terms of Eddington units on the y-axis for the two cases, 1% Eddington and 10% Eddington. OK, so what's going on with these spectra? The first thing I want you to note is that the low energy or thermal part of the spectrum obeys a mass scaling that we can understand fairly easily. Classical accretion disk theory suggests that the temperature should scale as m to the -1/4. And if you look at the temperature scaling down in this region here, or down in this region here, this energy, peak energy of the low energy thermal part is indeed scaling as m to the -1/4. OK, so we can understand this part, but this is not something that we can actually observe. So what can we observe and compare these spectra to? The first thing is the iron K-alpha region. So this is this little bump over here. And there is a tiny little bump over here as well, but it's less visible. So I hope you guys can see this bump here. And I'll be talking about that a little bit later as well. And the next thing that we want to compare to is the continuum slope. So this is a log-log plot. So this slope here is a power law. And we want to compare this slope to actual black hole accreting systems that are observed by X-ray telescopes. And finally, we want to look at this part of the spectrum. This is called the high energy cutoff. People claim to be able to observe this. It's kind of unclear whether or not they actually can, but the values that they find are consistent with values that we find. So maybe they're really doing it. Okay, so I'm going to split the different mass models into two groups. There's stellar mass accreting black holes, which are a black hole and a stellar companion, and also AGN mass, which are the supermassive black holes at the center of galaxies. Okay, so in the stellar mass case, the continuum slope is quite complicated. This diagram on the right is a hardness intensity diagram. And so hardness is the ratio of high energy X-rays to low energy X-rays. And intensity is just the overall number of X-rays. And so most X-ray binaries have 2+ spectral states, a low hard state over here and a high soft state over here. And where do our models fall? Well, they are both hard. So we have a model which falls directly into the low hard state, and then one which is more consistent with the intermediate hard state. But let me just say that every X-ray binary is unique. There are many ideas to explain this cycle, and this is just a schematic. You know, there are many X-ray binaries which go over here and which go this way. So every X-ray binary is unique, and we don't really know what's going on. But at least we have models which are consistent with the hard state. Okay, in the AGN case, this is showing an E rho zeta spectrum for all of the AGN that they've observed. And what they find is a spectral slope of about 1.9, so 1.5 to 2.3. And we find, a spectral slope of 1.8. So we're kind of sitting right in the middle of their distribution. And they also find this excess luminosity in soft X-rays, and by that they mean under 1 keV. And this is now showing our models, but fitted to a power law, and then in the bottom you see the residual, so model minus power law. And what we're seeing in the left-hand part of this plot at sub 1 keV energies is this same ubiquitous soft excess, both in comparison to the power law itself, and in particular in comparison to the stellar mass models, which is this black line here. So if we compare this red, yellow, and orange lines to the black line, there's a huge difference in slope. Okay, we also investigate a question in this paper of why AGN of all masses have similar spectral slopes. And so if you look closely at this figure, and you look specifically at 10 to the 6 through 10 to the 8, so orange, red, and darker red, these are all kind of separated from the rest of the models. This is the case here as well. And why might that be? This figure is showing the flux coming out of the disk as a function of energy for different radial bins. So this is close to the black hole, this is far away from the black hole. And what I want to highlight is for the region closest to the black hole that is producing these most energetic X-rays, the 10 to the 6 through 10 to the 8 solar mass models have different behavior. So for this black line, you can see an obvious peak here. This is an iron K-alpha line, which is coming out of the center of the disk, whereas in these other models, there is no corresponding peak. And this is showing us that there is a lot of iron K-alpha absorption in these higher mass models, which is not present in the low mass models. This is causing the segregation in spectral terms and explaining why the AGN, so 10 to the 6 through 10 to the 8, have this distinct spectral slope when compared to the other models. Okay, I just want to show some preliminary results from another paper. These are K-alpha profiles for the 1% Eddington case from 10 solar mass up to 10 to the 8 solar mass. And I'm not going to talk about this too much because we're still trying to understand these figures. But I will say that these look a lot like observation, which is encouraging. I also want to highlight another preliminary result related to circumbinary disk spectra. So some fraction of AGN live in binaries. And for instance, as preparation for LISA, you might want to know how many of these AGN are actually binaries. So that's what we want to know. This figure here is showing our spectra not for a single black hole, but for a binary system. And specifically, it's showing the CBD disk, which is the region kind of outside of the binaries themselves. So it's not showing mini disks, but it's showing this kind of more further out region. And the idea is that can we look at these figures and find some spectral signature, which is a smoking gun of the binary case. And then that would allow us to then identify these binaries, which really hasn't been done yet. OK, so I will summarize by saying that we are doing radiation transfer post-processing of GRMHD simulations. And we're doing this in a way that solves for local thermal balance, which is something that other codes can't do. We're also taking into account detailed radiation physics in the disk, which allows us to do, which allows that local thermal balance in the disk. This is something that other post-processing codes, again, can't do. And we've found some interesting results, but we don't yet have all the answers to those phenomenological questions that I mentioned in the introduction. But finally, we do have a tool that can answer those questions. So thanks for your attention, and I'll take any questions now.
Do you have any questions from the audience? I have one. So when it comes to observing this high energy cutoff, I was wondering if you could expand a bit more on like what observers are seeing and like why there might be some doubt whether it's the cutoff or not.
Yeah. So generally, the higher you're very lucky if you can get an X-ray spectrum that goes beyond, say, 50 keV, and this cutoff is kind of located around 60, 70, 80 keV. So a lot of times people are fitting data which only goes up to 50 keV, and then they say we have a cutoff of 95. And so that's a little bit kind of hard to believe sometimes. But yeah, if your data is good enough, you might be able to see it. Yeah.
I saw the very back first.
Okay. Yeah, you raised this question about like what could be a smoking gun to find binary black holes just from the spectrum. Like, do you have any idea already what that could be?
No.
So there's no suggestion in there that you're...
I haven't had a chance to look in detail. I mean, what you'd hope for is that there's some periodic modulation of the spectrum. Of course, people look for this already in kind of already existing data sets. So the question is, can you find something that varies on observable timescales that people wouldn't have already found? So it's a little bit of a hard question, but we're hoping that we can get something.
I saw one of the students have a question.
Yeah. So I don't know if you can answer this question, but like, do we have like a specific, like how far the X-ray would be able to see? Like what's like the farthest it can possibly, or even theorize?
Yeah, right. No, that's a good question. I do not know off the top of my head. I remember there was a claim of an X-ray detection at redshift 10.6, which is like 13 point something billion years in the past, light years away. I don't know if that was ever verified. I don't know if anybody else remembers that. But in principle, we can see X-rays pretty far away. But in terms of doing this sort of analysis, we need lots and lots of X-rays so that we can create these spectra.
Any last question?
Cool stuff, Chris. I'm curious about the Rosita spectrum.
Yeah.
So was that, first of all, was that a stacked spectrum that you showed?
Yes.
Or was, okay, not a single object.
This is stacked.
Okay, and then is there like, I mean, how much are you worried about like a luminosity cut or some other observational cut that could influence like the detection of this feature or not?
I haven't really thought about kind of those kind of population statistical questions. Mostly, we are in the business of comparing to a single black hole spectrum. What was kind of cool about this Rosita paper was they, have these 17,000 sources, and it matches our data very well. but usually we're looking at a single paper. And so those, I think the question you raise is sort of more advanced than we've looked at so far.
Let's take Chris again.
There's one more question.
I was just curious about the low resolution, low energy data that you were showing. You said something that you couldn't see it.
Yeah. So it's because it's in the UV. And so observationally, it's a little bit challenging because there's hydrogen, which is blocking it. But
higher redshift, redshift into your bandpass and that sort of.
Yeah, that's true, and that's something that we're looking at.
Might be a fairly reasonable diagnostic in terms of.
Yes, I've also slightly misled you though, because this is not what the actual spectrum would look like in real life. There should be some kind of continuation up into the optical, and this is coming from further out in the disk than we have GRMHD data for. We only can simulate out to a certain radius because of computational constraints. These things are expensive to run. But if you were to simulate out further, then you would be able to get lower energy photons from further out in the disk, and so it would probably go something like this. So this part of the spectrum in particular is not something that we would think that we would be able to observe.
It would be very important to know what it is, mainly because it contributes to the ionization.
No, yeah, that's a good point. Yep.
All right, sorry, we need to move on to the next speaker, but if you have any questions, feel free to ask Chris after the talk.
Okay.
Our next speaker is another JHU postdoc, Francesco Iacovelli. So let's hear about what he got to say about compact optics.
Yeah, should I change the slides though?
If you're
Where is it? Oh, here. Great. Okay. Hi everyone, I'm Francesco from Upstairs, postdoc in Emanuele's group, interested mostly in gravitational waves and cosmology. That's what I'm gonna talk about today, after first of all thanking the organizers for giving me the opportunity of talking here. And also thanks for the introduction to black holes. I don't have to make it now myself. Great. You also saw a chirp already, that's beautiful. Now, in the title, there's a bunch of words, third generation detectors, bright sirens. I'm gonna try and explain what I mean with those, and then giving some forecasts and some predictions of what we can do for cosmology with those handles, starting from third generation detectors. So what is the future of gravitational wave science in terms of instruments? Now, this is something you didn't see before. I'm very glad about it. You saw a chirp. That's actually a collection of all the 90 events we observed up to the third observing run of LIGO, Virgo, and Kagra, the four gravitational wave observatories that we have running now. Some known guys, that's each dot here is a binary that we observed merging and emitting a burst of gravitational wave radiation. Here on the y-axis, you have the masses of those binaries. So it's tens of solar masses for most of the black holes, up to 100 for the most massive. Here we have the very first detection that got the Nobel Prize soon after. And here, it's the very first binary neutron star event and multi-messenger event. And that's crucial for me because it's most of what I'm going to say afterwards. So some event for which we saw both the gravitational wave burst and some electromagnetic burst immediately following the gravitational wave emission. And let me also mention that the detectors are running now, and as of now, there should be, I checked this morning, 211 new candidates coming out part by the end of the summer, part afterwards. There might be some new one also, if it's 212, 13, that's about it, but that's what we did now. Are we happy? No, we want more. clearly we want more, and because we started just scratching the surface of what we can do with gravitational wave science, and that's why since many years actually people have started to think about the third generation of gravitational wave detectors. The European project is called Einstein Telescope. And what are the advancements? What makes a third generation detector? In particular, the bigger facility. The LIGOs now in the US are 4 kilometer long, have interferometers with 4 kilometer long arms. Einstein Telescope should be 10-ish, 15-ish. This expands, this lowers the sensitivity, improves the sensitivity, we'll see later. Plus some new fancy things like going underground for the Einstein Telescope, because it's counterintuitive, but the more you go deep in the soil, the less you have seismic noise, and that's what's killing you at low frequencies. So we go deep, and then we have actually a design with an interferometer optimized for high frequencies with a higher laser power, and something optimized for low frequencies, which instead is cryogenics, higher suspensions to handle better the mirrors. That's ET. Here's a bunch of references. I think there might be maybe the slides shared that's somewhere. You can click on the links. On this side of the Atlantic, instead, we have Cosmic Explorer. That's essentially an even more scaled up version of LIGO. So instead of being potentially a triangular detector as ET, but for ET we're also considering 2 Ls, this should be L-shaped, so standard interferometer, but bigger, meaning 10 times bigger than LIGO, 40 kilometers. This will sit on the surface, so ET is better in a sense at lower frequencies. This would be better in the bucket of the sensitivity. We'll see in a second what I mean. Plus some newer fancy things like squeezing and things I will not, I don't have time to talk about, but are very interesting. There's lots of people working on that. Now, why do we need them? Because here is the noise amplitude spectral density. So that's what's your noise floor in a sense. So the lower you go, the lesser the noise, the better it is. And with current facilities, even pushed at the maximum that they are supposed to get to, we go to the 10 to the minus 24 square root of Hertz. That's great, but with third generation, we go 1 order of magnitude deeper. And why do we care about this order of magnitude? Because gravitational waves are a strain. They are not a flux. So they scale as 1 over the distance. So if we gain a factor of 10 in sensitivity, we can see a factor of 10 in farther away. And in terms of volume, that's a factor of 1,000. So in terms of the redshift, for example, we are going from redshift something-ish with current detectors up to redshift of potentially 100, observing binary black holes, if there's any, might be primordial, we don't know, in case we get there. And for BNSs, we can get up to redshift 3, so after the peak of the star formation rate. Also, thanks to the improvements at lower frequencies, we also open some other windows, like more massive black holes, intermediate mass black holes potentially, or also subsolar candidates on the other side. Another more pictorial way of sketching this is with second generation detectors. We are a redshift 2-ish, so there's most of the galaxies and structures that we see today. The target of 3G is the dark ages, where there was almost nothing formed. So that's one of the reasons we want to get there, but actually the science case is made up of a lot of things. I could explore a bit some of them. Cosmology is just one, but we are gonna study the demography and evolution of black holes and neutron stars, also the composition of neutron stars. There's synergies with other observatories, both gravitational wave and electromagnetic. In other bands, like LISA is supposed to fly, that's been mentioned, is supposed to fly in 2035. It should go in the mid-years. There's other experiments that should cover the DESIERs, like the Lunar Gravitational Wave Antenna, which I recently joined. It's very nice. Potentially detecting new kind of sources, not just binaries in spiraling, but also pulsars with some degree of ellipticity. Core collapse supernovae, they are dimmer in gravitational waves than binaries, so we need really a lot of sensitivity to detect them, and stochastic backgrounds. And also, apart from the astrophysics side, there's the fundamental physics and cosmology, because we can do exquisite tests of GR. both in spiral, so at the level of the post-Newtonian expansion, and going closer to the merger and near horizon physics, testing the nature of the compact object itself, for example. And then on the cosmology side, we can understand, for example, if some of those binaries might by chance be primordial. That would be a candidate of dark matter, for example. Or not all cosmological models would produce primordial black holes or other candidates, or also in the cosmologist side, study the dark energy equation of state at higher redshifts that are accessible to these instruments, or effects like modified gravitational wave propagation, which are exclusive to the gravitational wave sector. So we wouldn't observe them with electromagnetic means. Now, that's why we need a couple billions to build third-generation detectors. Now let's go to the bright siren side. So what can we do for cosmology? Why gravitational waves are so interesting for cosmology, and what got me at first working on gravitational waves, is that they are standardized objects by definition. So we know what's happening. It's a binary, two objects in spiraling. We can predict what's going on in the radiation frame, in the source frame, and move to the detector. And for example, if we look at the peak luminosity of the gravitational wave emission, that's actually independent of mass, because it scales its flux, so energy in a given amount of time, and both scale as the mass, so it cancels out. There's a residual dependence on the mass ratio, but forget about it. And so for a gravitational wave signal, almost all of them will have a peak energy of 3.7 10 to the 56 ergs per second, which, to put in perspective, is 10 to the 23 times the luminosity of the sun, or 10 to the 11 times the luminosity of our whole galaxy. And indeed, if we pick the very first detected gravitational wave event, you saw the chirp before, that's the signal, that's the strain actually in the band, the peak luminosity for that guy was 3.6, 10 to the 56 ergs per second. Perfect. And it was slightly non-equal mass, that justifies the light shift. Perfect. So we know something for which we can compute the luminosity distance. Because if you work out the GR equations and then you build some numerical relativity simulation and you fit some waveform model, which is easier to, some approximate model to that, which is easier to handle, then you have your strain. From the time frequency evolution of the strain, the phasing and everything, you reconstruct the intrinsic parameters of the source. So how massive it is, how the black holes are spinning. Then from when it gets to the detectors, you can do triangulation, so you can understand where it was in the sky, how it was inclined, for example, also. And you're left essentially with this 1 over dl. And that's the kind of observable you want. But there is at least for the dominant harmonics in the gravitational wave signal, there is a kind of strong degeneracy with inclination angle if you are at small inclinations. We'll see later why this is an issue. And that's why they refer to as standard sirens, because they're something standard. And they are sirens because gravitational waves, essentially, they cannot form an image. The wavelength is bigger than the size of the source, so it's more something like aural, and they can be better thought of as sound, in a sense. We can literally, actually, for gravitational ground-based detectors, we can translate all those gravitational wave signals into sound, one-to-one. Now, once we have DL, for cosmologists, usually DL is tough and redshift is easy. Opposite situation with gravitational waves, we have DL easy, we need the redshift. What can we do? There are several ways. I will sketch some, but the point is that once we have both, there is a luminosity distance redshift relation. It depends on some cosmological parameters. We feed in our data, and we reconstruct the cosmological parameters, including, for example, the current expansion rate of the universe, H0, the matter density in the universe, radiation, dark energy. If you want to include modified gravity, whatever you like, you feed in there, and you can get constraints on those parameters. The problem then is the redshift. The most straightforward way is if you have an electromagnetic counterpart. That's what I'm gonna focus on for the rest of the talk. That's the easy way in a sense. So some electromagnetic radiation accompanying the gravitational wave emission. You detect it, you localize it, then you pinpoint your telescopes. There is a single galaxy, hopefully, or a few galaxies. You have the redshift, and you do your estimation. If you don't have access to that, there are statistical techniques. They are a bit more challenging. One, for example, is using a galaxy catalog. So you statistically associate each galaxy in the localization region of a gravitational wave event to the gravitational wave event. Statistically, this will converge to the right H0. Or you can look at the mass distribution of the sources, because the mass, the wave is redshifted. So the mass that you infer is the source detector frame mass, which is 1 plus z times the source frame mass. So if you have some knowledge of the source frame mass distribution, you have 1 plus z. And then there's a bunch of other techniques, like using the tidal deformability. I really don't have time for that. Now, easy way, electromagnetic emission. In this case, we can have either neutron star black hole systems or binary neutron star systems, because two black holes won't emit any light, no chance, unless they are in some dense environment, but that's a bit more difficult to model. So what happens if we have a BNS? The binary is in spiraling, the objects get deformed, part of the material is expelled. There's a bound component and an unbound component as the binary evolves. The bound component accretes back onto the merger remnant and powers eject. The unbound component propagates, and then there's a shock propagating after the merger that eats it up, and that's a kilonova. So essentially, that's two kind of things that we can detect following a BNS merger. GRBs are a bit easier if they are on axis, because they are more powerful. Kilonova is a bit dimmer, but it's isotropic-ish. So we have the production then of a gravitational wave plus the electromagnetic emission. We detect both. We pinpoint a single galaxy thanks to the electromagnetic emission. We have our Z, BEM, and we do get an estimation of H0. That's for a single event. The very first that I showed at the beginning, GW170817, which was associated to GRB 170817A, and then associated to a single galaxy, which should be NG4993, I think, something like this. And we got a 15% measurement by itself of the current expansion rate of the universe. This guy was at very small redshift, was at 40 megaparsec. So the only thing we could estimate is H0, but still makes the point. Now, that's current detectors. Unfortunately, in 04, we had no other multi-messenger detection and no other BNS detection, actually, and SMBH, yes. But that's also motivating even more why we need 3G detectors, because at 3G detectors, we are going to detect really like 10 to the 4, hopefully, 10 to the 4 BNS systems a year, order 10 to the 4. Some of them will have exquisite localization, and we have chances of detecting order thousands of systems with an associated kilonova, or tens to hundreds of systems with an associated GRB emission. Clearly, this is detectable, doesn't mean detected. That means that the electromagnetic facilities, like the Vera Rubin, is not pointing at all, it's not following up all the gravitational wave candidates. That's not going to happen, but we are trying to make friends. But it's still a possibility, and we still have a very high rate of potentially detectable sources. Another more pictorial way of observing this, it's this plot that came up recently in some of our work. Here, each yellow dot is a BNS detection in the gravitational wave sector. Each red dot is an associated kilonova detectable, and each bluish flare is an associated GRB detectable. So we can, with kilonova, we mostly get to redshift 0.5. That's where we can get. But with GRBs, we can go way out to redshift of 2-ish also. And also at 3G detectors is not only the rate, but also the estimation of the luminosity distance is going to improve by orders of magnitude, potentially to the sub% level. You put all those things together, and for example, from kilonovae, you have that with a year of observations, you go down potentially to a sub% level accuracy on the Hubble constant, and omega matter is also pretty well constrained. With GRBs, you do a bit worse, because they are higher redshifts and they are less. So the constraint is milder, but, oh no, I forgot a slide. Oops. I'll say it in words. They are better at constraining, for example, the dark energy equation of state, because they can be seen at way farther away. So they're in a sense very complementary. Plus, as I said before, you can open up the parameter space, impose some prior from electromagnetic observations, and then you get very interesting constraints, for example, on the modified propagation and some gravitational wave-only effects that modify GR at cosmological scales. And again, here GRBs are exquisite because they can probe this thing up to very high redshift. Now, in the few minutes that I have left, I'm going to talk about one potential issue with GRBs. That's all forecast, that's all easy in a sense because we know what we injected. The problem with bright sirens when you move and try and apply to real data is that for sure the accuracy is expected to be exquisite if you have order 50-ish detections already. But the moment you shrink the accuracy, the moment the statistical uncertainty goes down, systematics start to be relevant, and you have to model them properly. In particular here, in gravitational wave, the calibration of the detector can be problematic at that level of accuracy, but there's hopes that this is going to be solved. Then there's peculiar velocity corrections when you estimate the redshift, especially if the system is at low redshift. And then there's what we have been working on for a while, that is the electromagnetic selection for GRBs. Because GRBs are beamed, you don't see a beam if it's off axis. You see it only if it's on axis. The problem is that you don't know how this beam is made. What does it mean? That, okay, suppose we are simulating now the events. We have our very first event, like our GW170817. This is actually more extreme than 170817 because that one was seen more off axis, but that's a simulation. So we have this event. The actual injected parameters lie in a corner of the parameter space. That's just the geometry of the gravitational wave posterior for DL and inclination. You saw before why we had a problem. They are strongly correlated, especially the 1 plus cosine squared over 2 and cosine a small inclination, they're comparable. So you can disentangle the two polarizations. So if you were to do the gravitational wave analysis only, fixing the redshift by the electromagnetic emission, you would put this dot here. Now, you add another one, same problem. Start deviating. If you draw a line here, it's not really working out. You add another one. Yep, again, same problem. You add all 50 of them. No way that if you just draw a line around here, you're gonna get an accurate estimation of the cosmological parameters. Now, this thing can be partly solved if you only focus on if you focus both on gravitational wave observations with and without a counterpart. But actually, we found a more natural way, that is, hey, let's model also the electromagnetic detection probability. That's the problem, no? That's the point. We can only detect GRBs up to some angle. We don't know the angle, though. Let's infer it. There will be some beam geometry of the jet. We can try and feed it into our analysis from GW plus EM, see what we get. And the actual funny thing is that you get a detection probability here. I'm not trying to fool you. That's a likelihood. The detection probability of detecting something that you detected is 1, true. But only if you know the detection process. If you don't know the detection process, the idea is that this gives you a further prior in a sense, because the idea is I detected a GRB, I know the inclination should be small, I don't know how small. That's the detection probability. So the detection probability of detecting something that you detected is 1 asterisk. Okay. you model this. I'm not gonna go in the details of the simulation. Nice thing is that you get an unbiased estimation of H0, and the bias would go up to more than 3 sigma when you pile up even 50 events. Plus, you reconstruct also the GRB parameters, like if you assume a Gaussian jet profile for the GRB, you can reconstruct the jet aperture of the jet, the aperture of the jet. And that's correlated with H0. That's why we had the problem before. And that's with this modeling, actually, we can solve it. And this is only 2 parameters. We are sampling a very large parameter space, actually, with all other cosmological parameters, the mass distribution of the BNS's rate, everything. And I guess I don't have time for that. So, sorry. It's a bit long.
Got a question over there?
Yeah.
I'm trying to understand how you get the much greater sensitivity to multi-messenger mergers on the photon side.
On the photon side, we just, so if you look at the limiting factor now is the gravitational wave side, in a sense.
Well, that means LIGO has found quite a number of binary neutron star mergers, but only one, 170817, was close enough to get good photon observations.
Mm-hmm.
So when you go to T or CE, you'll get lots of more gravitational wave events, but we still have the same telescopes.
Well, Rubin, for example, was not...
Right, it's a 4-day cadence, so you won't necessarily pick it at the peak.
Sure.
And
but the limiting...
how much advantage does that give?
So what we did here was to be agnostic and say op. Here, the limits that we imposed were really on magnitudes or flux densities. That's for Fermi GBM. That's something we have now, and you still go from 0 that we had up to now in 04 to 37 with something that we have now. And the people are developing new instruments that should be also not entirely devoted, but with a strong component of follow-up for multi-messenger and for GRBs, like TCUs. It's an European mission. So yeah, we are going to improve also on that side.
Also, hope that Fermi is still operating by the time any of these experiments is built.
Let's hope so.
At the moment, we are concerned about whether it will operate next year.
That's not the concern only on the electromagnetic side.
Right. Sorry, this is a little bit tangential to your talk, but could you say a little bit more about the gravitational wave only distance that you get, and how many events would you need to get a reasonable constraint on the shot?
So the accuracy is actually getting interesting already now with LIGO and Virgo, because with 90 events, most of them, but 4, where BBHs, they are starting to be more competitive with the GW 170817 only constraint on cosmology. The moment you move on to more and more detection, that's going to be very helpful. It depends also on the kind of detections. For example, for the first part of 04, Virgo was not in operation. This means that you localize more poorly in the sky because you have only 2 detectors in the US. And clearly, in turn, if you want to apply some method with the galaxy catalog and get some host in a broad localization region, that's not optimal. So you can get to, with some so-called golden dark siren, that is a gravitational wave event measured so well that there is only 1 galaxy in the localization region, you get to 2% with 2 events. And that's gonna be doable in a decent amount of time. It's
doable in LIGO Virgo.
A sharp, if any, with the future upgrades.
Okay.
Not now.
Yeah, I think it's a similar question to the first one, but from someone who's very naive about the field. But I'm interested in the EM counterparts, because you made a big deal about the redshift increase that third generation observatories are going to see in terms of gravitational wave detection. But how are we going to do as well with Because what kind of redshift error can you tolerate when you're trying to estimate the cosmological parameters? Because at some larger redshift, you're going to get, even with Spectra, you'll have some small redshift error. With photometry, you might have a big redshift error, you might have catastrophic failures.
No, but
so as you go to higher redshift, what are the prospects?
No, but indeed that's. So I focused only on one kind of sources. That's the bright sirens. The dark sirens can be more promising as you move to higher and higher redshifts. If you start and have quite a crapload of events, that's what we hope to have with third generation detectors. In that case, you get most of the constraint just from the gravitational wave events, from knowledge of the mass distribution of the gravitational wave events. With the electromagnetic counterpart, as you see here, also with Rubin, Kilo 9, we stop at 0.5. We don't hope really to go better than that. But what's the problem now is that at the moment, we are very limited by the gravitational wave detection. That's why I made a big deal out of it. Because now we've seen one, sure, second potential BNS, even though the second mass is pretty high. 2 NSBHs up to 3, and potentially 2 or 3 now. NSBH though, BNS 1 or 2. So that's what's limiting us now, not really the point. And that's why I made a big deal out of going to high redshift with a BNS. And even for 3G with BNSs, you go to redshift of 3-ish. So if you want to really go deeper than that, you only have the dark part, you only have the black holes, and you need the statistical techniques. They are more difficult though because you need a lot of statistics. Sorry, it's sort of a pun, but.
I think that's about all the time we have. Let's give both our speakers a round of applause.